In this video, we're going to look at collision model and reaction profiles. Okay, so let's go ahead and have a look at a simple synthesis reaction. Let's go ahead and we've got some hydrogen, some H2 molecules colliding with some iodine. It takes some energy and then it's in equilibrium with two hydrogen iodides. So here we've got the green hydrogen, the diatomic hydrogen, the iodides. It takes energy once they collide to form the products. So we can look at this with a reaction profile. So let's go ahead and keep our reaction up here to remember what we're doing. And then what we can see is our reaction profile is going to look something like this, where here is the energy and here's reaction progress. We start over here with our reactants and you can see that they're at a lower energy. The products are at a higher energy. See, that shows that we've put energy into our reaction. So our reactants form products. The products have a higher energy, and that is shown in the equation by putting an energy here on the reactant side. Okay, well, what is this big hill in the middle? Well, that big hill is what we call, it's the amount of energy that has to be overcome for those reactants to turn into products. And every reaction has this, and it's called the activation energy. So that's the amount of energy it takes to go from where your reactants start in energy to get to the very top of that hill. Every reaction has to get over that activation energy in order to form products. Now, the very top of that hill, older chemists called it a transition state. It's also known as the activated complex. That's the very top of the hill. And at the top of the hill, that is where those reactant bonds, those H2 and I2 bonds, are breaking and forming the HI bonds, the product bonds. So the transition state, the activated complex, there is a lot going on. That's where bonds are breaking and where bonds are forming. All right, so here we've got our reactants, our diatomic molecules, the hydrogen and the iodine, and over here we have our products that have formed, and that is the hydrogen iodide. All right, now we know from equilibrium that we've been doing that these reactions are reversible. So let's look at the forward direction first, and this has a delta E for the reaction. So it's from where the energy started to where the energy at the end of our reaction. That's called the delta E, sometimes called delta H. And we can see that that is going to be a positive value because delta means final minus initial. And so our final energy is higher than our initial energy where we started. So this is when a delta E is positive, and that is what we call an endothermic reaction. And so as we saw from our reaction here, we put energy in. So that's endothermic. We put energy in and our delta E is positive. In other words, the energy of our products is higher than the energy of our reactants. All right, now let's talk a little bit about what had to happen for those reactants to form products. How did they get over the hill? Well, we know that they had to collide. And so this is called the collision model. And we've been talking a lot about this. Mr. Grundon's been talking a lot about this with you in terms of Le Chatelier's principle. So in our collision model, the molecules must collide to react. And not only do they need to collide, that's not enough. What if they collide and they only make it up part of the way in energy up the hill? They're not going to get to the other side. They would just fall back down in energy. What's going to happen? They must collide with enough energy, and if they have enough energy to reach the activated complex, then the bonds will break, the bonds will form, and they'll form products. So collisions aren't enough. They have to collide with enough energy to reach that activated complex. They have to collide with the right orientation, and the timing has to be right. So that's what has to happen in this model for our reactants to form products. But once those products are formed, and as that concentration starts building, they'll start colliding together, and then it can reverse and form back to our reactants. Now let's look at this in reverse. So if our products start colliding, they also have a hill they have to get over, but that activation energy is lower than the activation energy for the forward reaction. Remember, the activation energy is the amount of energy it takes to get to the top of the hill. And so this reverse reaction, the activation energy is a little bit lower. But notice something that stayed the same. The magnitude of delta E stays the same. The difference in energies between the reactants and products is the same. However, the sign of delta E is different. Notice that your reactants are lower here in energy than your products, but if we're going in reverse, final minus initial would give us a negative value. So this reverse reaction, delta E is negative, and we say that it is exothermic. And so if we have the 2HI going back to hydrogen plus iodide plus energy, energy is being given off. And so you can see here the energy is lower where we end up. Okay, so let's make sure that you understand that if delta E is positive, like in the forward direction, if delta E is positive, it is endothermic, and that means that at the end, our energy is higher than where we started. And if it's endothermic in one direction, it's going to be exothermic in the other direction. Okay, now let's go ahead and look at an exothermic reaction. What does a profile look like for that? And here we've got an exothermic profile. Notice our reactants are higher in energy, the products are lower, so the delta H for this reaction would be negative. And so we would have energy being given off, so energy would be on the product side for this one. Now, how does a catalyst speed up a reaction? Does it make collisions happen faster? Well, no. What a catalyst does is it lowers the activation energy. So this red line here, see how the hill is lower than what it had been previously? A catalyst lowers the activation energy, and we'll learn why in a unit later on. It doesn't change the delta E of the reaction. All that a catalyst does is it changes the activation energy. And so now the activation energy is lower in the forward direction and in the reverse direction. So, did you learn that in this video, did you learn that molecules colliding must have enough energy to get to the activated complex? Did you learn that a catalyst speeds up a reaction by lowering the activation energy, and the delta E of the reaction doesn't change? Reactions that are endothermic have a positive delta E, and it looks something like this, where the energy of our products is higher than our reactants. Reactions are exothermic, they have a negative delta E, and the profile looks like this. And if a reaction is endothermic in one direction, it is exothermic in the other direction. All right, well, we'll see you tomorrow.